some of the properties of this operator. For example, delta operated on some constant will obviously give us 0, because delta of fx is equal to c, say delta of c is equal to c minus c, this is 0. Delta operated on some constant multiplied by a function will be equal to c into delta fx. Delta satisfies the distributive law. If we have fx, frx, f2x, etc. all continuous function, then delta operated on their sum or subtraction of this operated on this will give us the delta of f1 on x plus minus delta of f2x, etc. Delta on the product of two functions. If delta is operated on product of two functions, say fx into gx, then we will get fx plus h into delta gx plus delta of fx into gx, that is equal to gx plus h into delta fx plus fx into delta gx. Delta operated on the rational function fx by gx. This result is given by this formula. So we have some operation delta operated on delta to the power n, that is, it follows the laws of indices. Delta m operated on delta n fx will give us delta m plus n on fx. This follows the laws of indices. If kth order forward difference of a polynomial of degree n, which is greater than or equal to k, it is a polynomial of degree n minus k. So if we take the differences of a polynomial of degree n, then its order will be lessened by an amount of k. So if we operate on second order difference on a fourth order polynomial, we would get a second order polynomial. If capital Px is a polynomial of degree nth degree, then delta of nth is a constant, and obviously delta n plus n acting on Px will be equal to 0. The converse of this theorem is also true. For example, if delta 5 on fx is a constant, then fx is a polynomial of degree 5, and if delta 5 fx is equal to 0, then fx is a polynomial of degree at most 4. Next we come to the shift operator. Similarly, shift operator also satisfies the distributive law. Shift operator operated on f1x plus f2x, etc. will give us shift operator on f1x plus shift operator on f2x, like this. Shift operator also satisfies the laws of indices. En operated on En fx will give us E of n plus n fx. For any constant k, E operated on k into gx will give us k into E operated on gx. Now some relationship among these operators. These are very important relationships. Delta into forward difference delta into backward difference delta will give us the difference between forward delta and the backward delta. There are some operations such as the relationship between E and delta. E shift operator is equal to delta plus 1. And similar relationship, these are the very important relationships, and there may be more and more relationships which can be easily computed with the help of their definitions. There is another operator which is known as the differential operator. You may know it that delta differential operator is represented by d, which means ddx. D stands for ddx, that is derivative of fx with respect to x. This gives us f dash x, and d square fx is nothing but f double dash x, etc. Now, one important thing I would like to mention you, that we know that the exponential series e to the power x is given by 1 plus x square by factorial 2, etc. You know this series. Let us agree to write e to the power d. However, d is an operator while x is a real number. So, but we agree to use this definition that e to the power d is nothing but 1 plus d plus 1 by factorial 2 d square, etc. So d is ddx. Now E of fx is equal to fx plus h is equal to fx plus h into f dash x. How we have arrived this right hand side? This is simply by Taylor series expansion, and this Taylor series expansion, when written in the form of d, we get 1 plus hd plus 1 by factorial 2 hd square etc. on fx. This is done by Taylor series expansion using the definition of capital D, that is the differential operator. So we have e to the power hd into fx. Therefore, E is equivalent to e to the power hd, noting that E is equal to 1 plus delta. So 1 plus delta is equal to e to the power hd. These are the symbol we frequently use in our further analysis. Similarly, we can have sine hyperbolic hd, cos hyperbolic hd, like e to the power hd. Now, with similar operator, we may write mu into delta. What is mu? Mu is defined as half of e to the power half plus e to the power minus half as per its definition, and delta is e to the power half minus e to the power minus half. This gives rise to half of e to the power hd minus e to the power minus hd, which is, you know it, that it is sine hyperbolic hd. That is, sine hyperbolic hd is mu into delta, and therefore hd can be written as sine hyperbolic inverse mu into d. This relationship I am writing down here because we will find in many places that this expression has been used in your text. Now, difference table. Let us now construct a difference table let the given data point be like this: x is equal to 1, 1.05, 1.10. Note that all values of x are equispaced. The difference h is equal to 0.05 and the corresponding values of y are given here. Now, the difference table will be constructed like this. In the first column, we will write down the value of x. In the second column, the value of y. In the third column, delta y. What is delta y? How I have obtained this value 0.1698 etc. This is nothing but y1 minus y0. y1 minus y0 is delta y0. So this term is delta y0. The next term is 0.1794 etc. It is obtained as the difference of 3.35 etc. minus 3.1740. This is the delta y1. Similarly, we can write down the second order difference. It is the difference between the 0.1794 minus 0.1698, and we will get 0.00 etc. This is the second order difference, and we call it delta 2y0. Similarly, this term is delta 3y0, this one is delta 4y0, and the last term is delta 5y0. You will observe that the difference magnitude in the significant figure in the magnitude of the differences gradually goes down. Here it is of the order of 1, 2, 3, 4, 5, 6, 7. 7 significant digits are there, but it came down to only 5 significant digits, and at the delta 5 we have only 1 significant digit. Prior to that, with the delta 4y is correct up to only 3 significant digits. So usually in the difference table, as we move forward, the significant digit in the corresponding differences goes down. Similarly, backward difference table can also be formed in a similar way. For example, point 2 it is 0.201336, and for point 4 it is 0.41072, and at the last point it is 0.8, you have 0.888106. Now this one is backward delta y1 is given by the difference between y1 and y0. Similarly, delta square y0 is obtained from these two differences of the first order differences. And you may note that the backward difference, relationship between the backward difference and the forward difference, delta operated on y minus r of the rth order is nothing but backward delta, rth order backward delta operated on yi. So this is the important relationship between the forward difference and the backward difference. Now, one important aspect is the propagation of error in the difference table, and one important term is noise level. We should make a point of this, that noise level is very important so far as the construction of the difference table is concerned. One of the inherent assumption for finding a polynomial which interpolates a set of data xi, yi is that yi's are free from any type of error, bearing only the rounding of errors. Errors may be inducted into the data set through say gross error or human error. For example, in writing this value of y, instead of 8 we may write it down 6. This is the gross error or human error, and we don't have any place for human error. So gross error or human error, we assume that we should take much care of it so that no gross error or human error can be incorporated into the data set. But we cannot get rid of the rounding of error. The gross error or human error should be avoided. As per care should be taken, sufficient care should be taken for that, but we cannot get rid of any rounding of error at all. Now, what is the result that if we have rounding of errors? What the rounding of errors is there? So far as our earlier table is concerned, say this one, in this value of 3.17024 etc., there may be that the actual result is not 3.1740234. The actual result may be 3.174023369. Instead of 4, it may be 36359. We write 4, it may be 336. It may be 336. Instead of 36, we write 4. So this is the rounding of error. There may be a positive rounding of error also. Instead of 34, it may be 343, 344. So there are errors inducted at the last significant figure of the data set. These are the rounding of errors. So we cannot get rid of this rounding of errors, and that is why rounding of error should be taken care of. Suppose in the y0 value, we have a rounding of error of epsilon 0, epsilon 1, epsilon 2, etc. These are propagating along as we move along the difference table, and ultimately you will see that at the third level the error magnitude is gradually increasing. It can be estimated that the error in the computed value in delta kth order delta yi varies with the limit plus minus 2 to the power k minus 1 in the last significant digit. That is plus minus 1 putting k is equal to 1, plus minus 2 putting k is equal to 1, plus minus 2 plus minus 4 k is equal to 2. That is, there will be last digit will be inaccurate by plus minus 1 or plus minus 2 or plus minus 4 etc. in the last significant figure of the first, second and third differences etc. If the length is small, then gradually then successive difference gradually decreases. I have already told you that the significant digit in the successive differences gradually get down, and here we see that in the successive differences the error magnitude gradually increases. So it is expected that there will be a step when we face the situation that increase that the computed difference is of the same order of the errors. Computed difference are of the same error as that of the errors. This stage is called the noise level. Beyond that level, the error will certainly dominate the table rather than the difference part, and that is why for this reason the computation of differences is to be stopped just prior to that difference, only up to the noise level. When we have this can be achieved when we get in the difference table of one significant figure.